Hello, everyone, and welcome back to your YouTube channel. And welcome to this amazing video today. As you must be aware, my master students, they are taking a course about uh, power system analysis. And one very important subject in power system analysis is fault analysis. Fault analysis is extremely important because define very extreme conditions inside the power system. Specifically, if we are talking about what kind of one of these subset of fault, the short circuit. The short circuit is basically an transient event characterized by very high currents, typically very high currents, okay? Several times the nominal current in a general sense, okay? They are very specific cases, but I will not discuss that now. But today we have a very practical session, a very practical video. Today we are dealing with a numerical example related with short circuit analysis. Specifically today we are dealing with asymmetrical short circuit at symmetrical faults, okay? And here in front of you, you have a very basic example. I will be solving this example. And as you can see over here, a synchronous generator G, is connected to a synchronous motor by using a delta start transformer, okay? It's very interesting. It's a very basic example. This is an isolated power system. A single generator is providing power, supplying to this synchronous motor by using a transformer. And here, because we are interested on asymmetrical faults, we are dealing with very important conditions where the neutral connection to ground is extremely important. As you can see, the generator is a classical star connected where the neutral point is solidly connected to ground, okay? That means the impedance between the neutral point of the star and the ground is 0. On the other hand, here on the right-hand side, we have a motor, a classical synchronous motor, and there is a classical star connection in that motor. But in this case, the neutral point of this star connection is going to ground by using a 0 impedance, and that is what we call a grounded star connection, okay? Well, here there are some numerical data. As you can see, we are providing the positive, negative, and 0 sequence reactance for the synchronous generator. Remember the subscript 1, 2, and 0 refers to positive, negative, and 0 sequence respectively. And here we have a transformer, and the transformer, positive, negative, and 0 sequence, all of them are the same and 0.1 per unit, okay? And finally, we have here the reactance, positive, negative, and 0 sequence for the case of this synchronous motor, okay? Then we have a very interesting condition. We have a fault here, and that is the deal today. As you can see over here, there is a description, and the description say a voltage line to ground short circuits occur in phase A at the motor terminals point F when the voltage is 0.9 per unit at 0 degree phase angle, okay? What is saying here is that we have a very important asymmetrical fault. In this case, we have a line to ground short circuit, and this line to ground short circuit occur here at the bus bar number 2, point F, as you can see over here, point F, and previous to the fault, The voltage, as you can see, the pre-fault voltage or before the fault, the voltage is 0.9 per unit at 0 phase angle. There are three very interesting questions over here. The first one, calculate or determine the Thevenin sequence reactance or impedances. Let's say here impedances. During the faulted condition. And question B, determine the sequence currents at the short circuit location. That means positive, negative, and zero sequence. And finally, very important, determine the currents at the fault point. In this case, current A, B, and C, okay? This is a classical example, very simple, but this example will allow me to show you the calculation, short circuit calculations in a power system where there is an asymmetrical fault, okay? Again, I always say to my student, please create a graphical representation. A graphical representation is extremely important in order that you can understand properly the conditions and the situation of the problem that you are attempting, okay, to solve. In this case, we have a practical situation. We have a synchronous generator. We have a two-winding power transformer, delta star connected, solidly connected the start on this bus bar number 2, and we have the synchronous motor, okay? And what is the first step? Well, the first step is I will start from that graphic representation, and I will go for the positive sequence network, okay? The positive sequence network is moving from this single line diagram. You must remember this is the single line diagram. And the single line diagram is basically a drawing that will allow you information about the power system components, the connectivity between the power system components, and it's a graphical representation. But the network, the positive sequence network, is an equivalent circuit that allows you to perform calculations inside your power system. What I'm telling you is departing or starting from here, from the single line diagram, we can go to this network, and it's extremely simple. For positive sequence, the models are extremely simple because the positive sequence representation, line to neutral representation for a synchronous generator is the most basic system. It's basically the voltage behind the reactance. In this case, this is the positive sequence reactance of the synchronous generator. And something similar is happening with the synchronous motor. The equivalent model for the synchronous motor, we are using an ideal voltage source, and that is connected, series connected to a positive sequence reactance. In the middle, between bus bar number 1 and 2, we have here the reactance, okay? It's extremely simple. Then, what we need to do is to calculate the Thevenin equivalent impedance. To calculate the Thevenin impedance, you must remember that one step is to switch off all the voltage sources. In this case, we will have here the reactance, bus bar number 1. Here we have the bus bar number 2. And here we have the positive sequence reactance of the synchronous motor, okay? But because we are interested on the Thevenin impedance, the positive sequence impedance, you must remember that we need to switch off those voltage sources, and this is the equivalent model, okay? This is the equivalent model for the Thevenin calculation. We switch off those voltage sources, and now we have a linear passive network. And from that linear passive network, we are able to obtain basically the Thevenin impedance. Okay, Thevenin impedance will be extremely simple because here we have two reactants in series. Okay, we have 0.15 plus 0.1, and then we have that impedance in parallel with 0.35. That is this practical calculation over here. We have 0.15 in series with 0.1, then in parallel with 0.35, and we obtain here the positive sequence, Thevenin positive sequence impedance, okay? Now it's time to do the same for the negative sequence. And again, it's extremely simple. What we are doing is, this is the negative sequence model for the transmission line. This is the negative sequence model for the synchronous motor. And here on the left-hand side, we have the negative sequence model of the synchronous generator. If you remember from my classes, please watch the video on my YouTube channel about the classes, the theoretical aspects. During negative sequence, there is not voltage source in the model, and the reason is because the only active components are the rotating machines, the synchronous machines, and those machines, they are only able to deliver positive sequence. There are no voltage sources here, but it's extremely simple. Now we need to calculate the Thevenin impedance here, the negative sequence impedance here, and that is extremely simple because we have here two components in series, and then in parallel with the second branch, 0.45, and we obtain the negative sequence, okay? The total negative sequence Thevenin equivalent impedance. Well, probably right now, what we need to do is the final step. We have here positive sequence. We have here negative sequence. And now we need to obtain the zero sequence impedance. Zero sequence impedance is basically the most exciting when we are working with asymmetrical faults, because zero sequence is very important, extremely important, defining the path for zero sequence currents, okay? For zero sequence, you must remember, this is the synchronous motor. The synchronous motor is directly connected the neutral point to ground. As a consequence, here we have the zero sequence model of the synchronous motor. This is the zero sequence reactance of the synchronous motor, and there is nothing between the neutral and the ground point. On the left-hand side, we have the equivalent circuit, and this is the equivalent circuit for zero sequence components in the case of this beautiful synchronous generator. Here we are using the zero sequence reactance of the synchronous generator, and because this generator is star connected and the neutral point of this star is solidly connected to ground, there is a path here for zero sequence. However, the very defining and the very important point in this power system, in this example specifically, is related with the two-winding transformer. Because the connection of the two-winding transformer, the connection of the neutral point of these two-winding transformers define the path for the zero sequence currents, okay? In this case, we are dealing with a delta star connected transformer. In a delta star connected transformer, there are very interesting and important properties for zero sequence. The star, as you can see over here, the star connection has the neutral point connected to ground. That means that the star side of this two-winding transformer allows the circulation of zero sequence currents. But on the delta side, we have an issue because the delta connection is not allowing the circulation of zero sequence currents on the lines. And that is the reason for this open circuit here. The open circuit here between bus bar number 1 and the zero impedance of this transformer is because the delta connection, this delta connection, it's not allowing the circulation of zero sequence currents here in the line. However, inside the delta connection, there is a possibility for zero sequence currents. And that is the reason that here we are using this very important model for the delta star solid connected star, okay? There is an open circuit here. Here we use the zero sequence impedance, or zero sequence reactant in this case, and this is the model that we use here, okay? I highly suggest to my students, I highly suggest that you must check the zero sequence representation of two winding transformer connections. You must be aware about that, okay? It's extremely important that you must be aware about what is the circuit representation of the two winding transformer when you are calculating a symmetrical fault. Because here, as you can see, there is no possibility of zero sequence here, but in this side, it is possible to circulate zero sequence currents, okay? Well, the next step is very simple because this side of the circuit is not connected, and to calculate the zero sequence, Thevenin impedance, we have 0.1 J in parallel with 0.8, and we solve that and we obtain the zero sequence Thevenin impedance here, okay? For that reason, we have finished the question A, the Thevenin sequence impedance, positive, negative, and zero, okay? Next step. Well, the next step is we need to know the sequence currents in order to obtain the short circuit currents in this asymmetrical condition. To obtain the symmetrical currents, what we need to do, and I will highlight here, we need to appropriately interconnect the sequence networks. I mean, we have positive, negative, and zero sequence, and now the short circuits define how the sequence networks are interconnected. And from there, it's just basically classical circuit analysis, okay? If you watch my videos about short circuit analysis, asymmetrical conditions, you must remember this. You must remember that if we are working with a single line to ground fault, the sequence networks must be connected in series, okay? The sequence network are connected in series. And that is the next step. The next step is basically we will connect the positive. This is the positive sequence network. This is the negative sequence network. And this is the zero sequence network, okay? And because we are using a single line to ground fault, that means positive sequence, negative sequence, and zero sequence, they are in series. Well, if all those sequence networks, they are in series connection, it's easy to see that positive, negative, and zero sequence, they are the same. And that is a beautiful property of the single line to ground false. Single line ground to false, they are characterized because the positive, negative, and zero sequence, all of them, they are the same, okay? That is very, very interesting property. The second important thing that you must know is we can use here circuit analysis. And calculating the positive sequence current is extremely simple because there is a single voltage source over there and all the impedances, they are in series connection. And from there is simple to see dividing the unique voltage by the series connection of these three impedances, we will find the positive sequence current. And from there, we can use the numbers, and voila, we obtain the positive, negative, and zero sequence currents in this case, okay? As you can see over there, we have here the positive sequence current 2.169, and that is the positive sequence current, okay? To be honest here, we have finished the question B because we already calculated the sequence currents during the short circuit condition. Finally, the next step is converting these currents. You must remember that those currents represent the symmetrical components of the current, and we want the A, B, and C currents. And to obtain the ABC current, what we need to use is basically the Fortescue transformation, and that is basically using here this A matrix, capital A matrix. This is the transformation matrix, and this is a 3 by 3 matrix, a square matrix where the operator, A operator, is used, okay? Remember, the A operator, this is lower A, this is 1, the magnitude is 1, and it's shifting the angle by 120 degrees, okay? Finally, we obtain here, this is the fault current. The fault current is basically the current moving through the A, and we can see here that the current B and the current C, they are equal to 0 because this system is under non-low condition, okay? Well, this is the end of this example. This is a numerical example related with asymmetrical short circuit calculations. And here we use the symmetrical components defined by Fortescue in 1919 in order to calculate the single line to ground fault current, okay? Well, this is all for this video. I hope you enjoy. I hope you learn from this video. And if you wish, you can subscribe to the YouTube channel, to your YouTube channel, and in order that you can receive notification when I upload a new video. And also, if you wish, you can send some emails and comments. I appreciate all the comments that I am receiving and all the feedback. Thank you very much. I hope you find those videos useful and you learn a lot. Well, that's all for today. Thank you very much for watching. I will see you in the next video. Thank you. Bye now.